looking at an infrared source, a ceramic rod glowing at a temperature of 1200 degrees absolute. Your eye can see the visible wavelengths produced by this source, but cannot see the invisible rays of infrared radiation. This infrared radiation, which feels only moderately warm to your hand, provides the scientist with one of his most powerful analytical tools. The absorption of this radiation and its subsequent analysis produces an infrared spectrum, a fingerprint, just as characteristic of a chemical compound as a human fingerprint is of an individual. Infrared spectroscopy plays a significant role in the study of the structure of molecules, in the development of antibiotics such as penicillin, and in atomic energy studies. It is the major technique used for the analysis of the innumerable organic compounds produced by nature and by man. This film presents the story of infrared radiation. First, we will examine the nature of electromagnetic radiation, and then the absorption of infrared radiation by the rotation and vibration of molecules. Next, the instrumentation needed to obtain an infrared spectrum will be developed using animation. Techniques will be shown for handling gases, liquids, and solids. Finally, the importance of infrared spectroscopy in analysis and industrial research will be presented. First, we will consider the nature of infrared radiation and the place it occupies in the electromagnetic spectrum. The electromagnetic spectrum graphically depicts energy, which is propagated in wave fashion. Electromagnetic waves are often described in terms of wavelength lambda, or in terms of frequency nu, measured in wave numbers. The wavelength is usually given in microns, symbolized by the Greek letter mu. Besides being wave-like, according to quantum theory, electromagnetic radiation is composed of discrete units of definite energy content, called photons, or quanta. The energy of the photon is given by the equation E equals hc times nu, where h is Planck's constant. C is the speed of light, and nu is frequency in wave numbers. Thus, electromagnetic radiation consists of photons traveling in wave-like fashion with an energy content dependent upon the frequency of the radiation. When a photon interacts with matter of an equivalent energy state, the photon is absorbed. In the ultraviolet and visible regions, photons are absorbed by electrons shifting in the outermost orbitals. In the infrared region, photons are absorbed by the vibration of the atoms and the rotation of the molecule. Thus, the total energy of a molecule is a summation of the energy involved in the electronic, vibrational, and rotational transitions, plus the translational energy, which is the energy involved in the translation of the molecule through space. Thus, the total molecular energy equals E electronic plus E vibrational plus E rotational plus E translational. Since measurements in the infrared region allow us to evaluate the energy of vibration and rotation, we shall consider only the vibrational and rotational terms. The molecular model shown in space represents the chloroform molecule. If three intersecting, mutually perpendicular axes are passed through the center of gravity of the chloroform molecule, the molecule may rotate with respect to the three axes. The resultant rotation is best described using moments of inertia. The moments of inertia measure the effectiveness of mass in rotation. The moment of inertia about the x-axis is arbitrarily designated I sub A. The rotation of masses about this axis is equivalent to that to be shown for the z-axis. The moment of inertia about the z-axis is designated I sub B. Thus, I sub A equals I sub B for the chloroform molecule. The moment of inertia for the y-axis is designated I sub C. Note that this rotation is not equivalent to rotation about the x and z axes. Using moments of inertia, molecules are classified as rotators into four types. Symmetric tops, such as the chloroform molecule, where I sub A equals I sub B does not equal I sub C. Asymmetric tops, such as the water molecule, where the three moments of inertia are unequal. Linear molecules, such as carbon dioxide, where I sub A equals 0 and the other two moments are equal. And finally, spherical top molecules, such as methane, where the three moments of inertia are equal. The rotation of a molecule, such as methane, gives rise to rotational absorption bands. The small symmetrical bands result from the rotation of the molecule. The large band is caused by the vibration of the carbon and hydrogen atoms. Such bands are called vibrational rotational bands. From a study of the separation of the rotational bands, the moments of inertia may be calculated, and the energy term E rotational may be evaluated. Each atom in a molecule requires three coordinates to fix the position of that atom in space. For the water molecule, 9 coordinates are needed. For a molecule of n atoms, 3 n coordinates are required, and the molecule is said to have 3 n degrees of freedom. Translation of the molecule in space can be described by 3 coordinates. Rotation also requires 3 coordinates for non-linear molecules. 2 angles describing the orientation of a line fixed in the molecule with regard to the coordinate system, and a 3rd angle describing rotation about this line. The remaining degrees of freedom describe vibrational motions, motions of the nuclei relative to each other. Hence, there is a total of 3n-6 fundamental vibrations for a non-linear molecule. For a linear molecule, only 2 angles are needed to describe the rotation. Hence, there are 3n-5 fundamental vibrations. Thus, for a linear molecule such as carbon dioxide, there are 9-5 or 4 fundamental vibrations. These fundamental vibrations will be individually examined using animated molecules and recordings of the infrared spectra of these molecules. The symmetrical stretching vibration is illustrated by this carbon dioxide molecule. In this vibration, the carbon atom remains fixed while the two oxygen atoms move symmetrically toward and away from the carbon atom. If we place a plus charge on the carbon atom and negative charges on the oxygen atoms, no dipole moment results from this vibration. The recorder draws a straight line showing that no absorption band results. Such a vibration is therefore infrared inactive. However, in the case of the unsymmetrical stretching frequency, the carbon atom moves preferentially toward one of the oxygen atoms. A dipole moment is produced during the course of this vibration. For absorption to occur in the infrared region, there must be a change in the dipole moment of the molecule during its vibration. The result is an absorption band, as seen on the chart. The unsymmetrical stretching vibration is therefore infrared active. This is the bending frequency vibration. As in the case of the unsymmetrical stretching vibration, there is a dipole moment produced. An infrared band occurs, but at a lower frequency. Another bending vibration of carbon dioxide is nearly the same as the one just shown. In this case, the oxygen atoms are vibrating toward you. Since these vibrations are equivalent energy-wise, only one absorption band results. This band is said to be doubly degenerate. This last bending vibration completes the four fundamental vibrations of the linear carbon dioxide molecule. In the case of a nonlinear molecule, such as H2O, there are 3n-6, or three fundamental vibrations: the symmetrical stretching vibration, the unsymmetrical stretching vibration, and the bending vibration. All these vibrations are infrared active and produce three infrared absorption bands. In addition to the fundamental vibrations, the spectrum may contain overtone and combination bands. The overtone bands may occur at 2, 3, or 4 times the fundamental in wave numbers. Combination bands are simply numerical combinations of the fundamental vibrations. All of these bands make up the infrared absorption spectrum. Knowing the fundamental frequencies of a molecule, the vibrational energy contribution may be calculated. Similar to the case of the molecules just discussed, there is a characteristic frequency of vibration when two atoms vibrate together. This characteristic vibration is dependent upon the masses of the atoms and gives rise to an infrared absorption band. Such a band is characteristic of a so-called functional group. For example, the OH group in liquid alcohols causes a strong absorption band at 3 microns or at 3,300 wave numbers. The carbon triple-bonded nitrogen group in nitriles causes a strong band at 4½ microns or at 2,300 wave numbers. The carbon double-bonded oxygen group in ketones results in absorption at 5.9 microns or at 1700 wave numbers. A portion of the chart prepared by Norman Coltup of the American Cyanamid Company is shown here with the regions of functional group absorption underlined. All functional groups cause infrared absorption bands at certain definite frequencies or wavelengths. This is a powerful qualitative tool for the organic chemist. Organic compounds are best characterized by their infrared spectra. And large files of infrared spectra are available for comparison purposes. In the identification of unknown compounds, the infrared spectrum of the unknown material is compared with spectra in the card file. Usually, positive identification can be made in this manner. How are such spectra obtained? Just as a glass prism breaks down visible light into component wavelengths, which our eye sees as colors, in the same manner, a prism of rock salt breaks down invisible infrared rays into component wavelengths, which can be measured. A rock salt or other halide prism is one of the essential components of an infrared spectrometer. An infrared spectrometer consists of a source of infrared rays, a salt prism, a slit, a thermocouple, an amplifier, and a recorder. Infrared radiation from the source passes through the rock salt prism and is separated into component wavelengths. Each wavelength is individually focused onto the thermocouple by rotating the prism. Thus, the relative intensity of all wavelengths of infrared radiation may be sampled independently. As each wavelength strikes the thermocouple, its energy is transformed into an electrical current, which is amplified and fed to the recording device. In such a system, any sample absorbing radiation from the source will cause a change in the graph being drawn by the recorder. A plot of absorption versus frequency or wavelength makes up the infrared absorption spectrum, which is characteristic of the sample. In the initial development of infrared spectrometers, single-beam instruments were employed because of their inherent simplicity. However, water and carbon dioxide molecules normally present in the air cause severe interference from both the rotational and vibrational bands. To eliminate this interference, double-beam instruments were developed. In a double-beam instrument, the infrared radiation is split into two paths. One beam passes through the sample, while the other beam serves as a reference. The two beams are recombined through a system of mirrors and a chopping device. This single beam, consisting of alternate pulses of sample and reference radiation, is dispersed through the prism and is sampled by the thermocouple. thermocouple reacts to differences between reference and sample beam only. Therefore, if the intensity of the two beams is equal, no significant change will occur in the recorded image. Thus, atmospheric water and carbon dioxide bands are canceled out by the double beam system. However, if the intensity of the sample beam is reduced by absorption of a sample, the two signals may be unequal at times. The recorder then responds to this difference by drawing an absorption band. In actual practice, the optical path of a double beam instrument is more complex than has been indicated by the animated diagrams. With this instrument, atmospheric water vapor and carbon dioxide bands are completely eliminated from the absorption spectrum obtained. Gases, liquids, and solids can all be readily studied by means of their infrared spectra. Gas samples, which have been condensed as liquids or solids by a suitable freezing mixture such as liquid nitrogen, are allowed to warm to room temperature. On warming, the solid changes to a gas. The gas is then transferred from the vacuum rack into an evacuated gas cell. The cell is removed from the vacuum system. And the infrared spectrum of the gas is obtained on a double beam instrument. The spectrum reveals that the gas is pure nitrogen dioxide, uncontaminated by the other oxides of nitrogen. For materials with low vapor pressures, cells with an optical path as long as 40 meters are used. With this cell, constituents in smog can be measured in the parts per 100 million range. Liquids are placed in a demountable cell, which is assembled as shown. The windows are sodium chloride crystals. Lead or aluminum spacers from 0.01 to 1 millimeter determine the sample thickness in the infrared beam. The liquid is placed in the center of the metal spacer. The rubber gaskets prevent the rock salt windows from being cracked when the cell is assembled. This sealed cell is constructed in the same manner as the demountable cell, but has a fixed spacer of known thickness. It is filled with a hypodermic syringe. Only 0.2 of a milliliter, or about 5 drops of a liquid, are needed. The cell is sealed with inert plastic plugs. Sealed cells usually vary in thickness from 0.025 millimeters to 0.1 millimeters. These cells are used for both qualitative and quantitative work. To cancel out the solvent absorption bands, matched cells of identical thickness are placed in the two infrared beams. With this ingenious cell, the optical path can be continuously varied until perfect cancellation of the solvent bands is achieved. Spectra of materials such as greases or waxes can be obtained by simply putting a thin film on the rock salt window. If a material is soluble in an organic solvent, it may be dissolved, placed in a sealed cell, and the spectrum obtained. For aqueous solutions, windows of clear barium fluoride are available to use in demountable or sealed cells. Another technique for solids involves mulling the sample with a mineral oil such as Nujol and placing the mull in a demountable cell. The best technique for obtaining infrared spectra of solids was developed in the United States by Sister Stimpson of Siena Heights College and in Europe by Scheidt. About 1 milligram of the solid is intimately mixed with dried potassium bromide powder. A vacuum dye is partially assembled. Then the ground powder is removed from the capsule and placed in the metal die. The die is completely assembled and evacuated. Pressure is applied in a hydraulic press for about 5 minutes while the die is under vacuum. The die is then disassembled and the sample removed. A transparent disc of the sample in the potassium bromide is obtained. The clear disc of potassium bromide is placed in a suitable holder and the spectrum measured. The spectrum shows excellent resolution and interferences from solvents or mineral oil absorption are avoided. Quantitative analysis using infrared absorption is based upon Beer's law. If P0 is the intensity of the monochromatic beam entering the sample, and P is the intensity of the infrared beam after it is passed through the sample, then the ratio P over P0 is the transmittance for the sample. The percent transmittance is 100 times P over P0. Given the solute at a fixed concentration in the cell of a fixed length, the absorption law is log P0 over P equals a constant times the length times the concentration. The constant is a particular value for each solute. This constant and the cell length can be combined into a single constant. Thus, log P0 over P equals a constant times the concentration. Log P0 over P is given the symbol A and called the absorbance. Hence, at a constant wavelength, the absorbance equals a constant times the concentration. By measuring the absorbencies of solutions of known concentrations at constant wavelengths, a calibration graph can be prepared. An unknown sample can then be analyzed by measuring the absorbance at the same wavelength. Infrared absorption techniques are invaluable for following the course of a reaction. Here is a reaction being studied in the gas phase. Oxygen is being added slowly to a sample of pentaborane in an infrared gas cell. The pentaborane reacts with the oxygen to form diborane. By following the changes in the infrared absorption spectra during the course of this reaction, valuable kinetic data can be obtained. Complex mixtures are often injected into a gas chromatography unit. And separated into distinct components. These components are collected and transferred to an infrared cell. The components are then identified by their infrared absorption spectra, using the matched cell technique to eliminate the bands of the collecting solvent. Infrared spectroscopy plays an important role in many industries. At the General Foods Research Laboratories, scientists are seeking the answers to such questions as what substances give coffee its fragrant aroma, by investigating the infrared spectra of various components separated from coffee. In the petroleum industry, at the Texas Company, additives in gasoline are analyzed using infrared techniques. At the General Electric Research Laboratory, this scientist is studying the absorption of gases on surfaces using an infrared spectrometer. This investigation will add to the basic knowledge of how catalysts affect chemical reactions. Infrared spectroscopy has contributed much to the progress of science. It has given us insight into the structure of such simple molecules as water and carbon dioxide, and such complex molecules as penicillin. It has provided a new and rapid method of analysis and control. To modern science and industry, it offers both an eye to the unknown and an eye to the future.